The James Webb Space Telescope just released a spectacular new image of the debris disk around the star Fomalhaut. Astronomers used Webb to search for Fomalhaut's inner asteroid belt, but instead it found not one, not two, but at least three nested belts around the star. Fomalhaut was observed before at wavelengths ranging from visible light with the Hubble Space Telescope all the way to the microwave spectrum with ALMA. Hubble used a coronagraph to block out the light from the star to reveal its outer debris ring. And that gave the image this really cool Eye of Sauron vibe. At millimeter wavelengths, ALMA detected the outer ring as well. And this outer ring is the equivalent of the Kuiper belt in our solar system beyond Neptune's orbit. So, a team of astronomers used Webb to see if they could locate Fomalhaut's equivalent of our solar system's asteroid belt, which should orbit a lot closer to the star. That alone would have been a really cool discovery because it would have been the first detection of an exo-asteroid belt. But what they found instead was more like an extended asteroid disk that was surrounded by an even more unexpected intermediate belt. The observations were made with Webb's mid-infrared instrument, or MIRI, by a team led by Dr. András Gáspár of the University of Arizona, and their results were published today in the journal Nature Astronomy. So I was very happy to speak with Dr. Gáspár and two of his collaborators, Schuyler Wolff and George Rieke, who also just happens to be the MIRI science team lead here in the US. We talked about how these results may represent evidence of multiple planets, some nerdy details of planetary system formation, what happened to the former exoplanet Fomalhaut b, how the MIRI images were created, and even some additional images that NASA didn't release. So I invite you to get nerdy with me as we learn more about the rings of Fomalhaut. Thank you all for joining me today, and congratulations on your result. And am I seeing what I think I'm seeing? I think I'm seeing two, maybe three asteroid belts. Is that right? Andras, you're the lead author of the paper. Let's start with you.
Hi, thanks for having us here. Uh, I would put it slightly differently. The asteroid belt is quite well constrained within the solar system, right? And we define it as being at a certain thermal location around the sun. And what we're seeing here is a more extended system with an outer belt, roughly at the same thermal location as where our Kuiper belt is. It also has a component very close to Fomalhaut, which is a sort of an analog to our asteroid belt. What's really neat is that this asteroid belt component is way more extended than we have in the solar system. And we've also discovered this very narrow intermediate belt in the system. So it's slightly different than what we anticipated just based on thermal signatures from previous observations for the system.
So if I could break in, I think it's more
Yeah.
than slightly different. I think it's really different from what we anticipated because all the previous images showed nothing inside that outer belt. I mean, there's a great ALMA image, there's a great Hubble Space Telescope image, and there's nothing there. And so this is the fun of the new capability that you can go look at something and you go, wow, I never knew it would look like that. And to me, that was the impact this had.
Well, you're right. It is certainly very different than anything that certainly I've ever seen, let alone anything you've ever seen. But what were you hoping to learn about when you used James Webb to study Fomalhaut? What were your science objectives for this program?
So the primary objective of this program was to observe three different systems. The three systems were Fomalhaut, which you see results of right now, Vega, and Epsilon Eridani. The Vega and Epsilon Eridani observations are going to be coming up this summer, so we haven't seen those yet. And the primary objectives were to see where the asteroid belt components are located and how they look like within these systems. We knew from thermal signatures, so there has to be some material at similar thermal locations that we have in the solar system, but we didn't know for certain where they are and how they're spread out.
You mentioned thermal locations. What do you mean by a thermal location exactly?
Fomalhaut is a much younger, hotter star than the sun. And so you get dust that's the same temperature as dust in our own asteroid belt at wider radii, which allows you to see structures closer in thermally to the star than you would in something like our own solar system.
So, do you think that that's what you're seeing here? You're seeing the equivalent then of an asteroid, probably a more rocky population closer to the star, and then a more icy population further from the star?
Probably, yes. Another way to think about it is the asteroid belt is located at sort of the transition between the terrestrial and the giant planets, whereas the Kuiper belt is outside the giant planets. All of the material has been sort of pushed out as the outer planets migrated over the lifetime of the solar system. And so we're not just learning about the composition of the dust in the various belts, but also hopefully something about the history of the planetary system around Fomalhaut.
And to pick up on the thermal point, Fomalhaut is 16 times more energetic than the sun. And because the intensity of light drops off as the square root of the distance, that means you'd expect an asteroid belt at about 4 times farther out around Fomalhaut, which would put it at about 8 astronomical units. And that would be right at the very inner edge of right at the black thing, which is where things saturated. And so what we expected was to just barely eke out a ring right at that inner edge and then not see anything from there until we went out to the outer Kuiper belt-like ring that had already been seen so dramatically. And so you can see how shocking this image was compared with what we thought we were looking for.
You mentioned that this star is a lot younger than our sun. Do you think this is like a recently formed star, perhaps, that it still has some of its residual material? Or is this something that's actually right here in our solar system, but because we don't have infrared eyes, we don't see it?
It's younger than the sun, but it's still relatively old. We still consider it to be in the debris disk phase. So these are the debris of sort of the planet formation process. This is another reason why we're quite surprised at what a bright central source we have here. András alluded to this before, but we have upcoming observations of Vega and Epsilon Eridani. And the thing I'm most interested in is to see how diverse planetary systems are, because this looks nothing like what we would expect based on our own solar system. So is it our own solar system that's unusual, or is this the unusual case? We don't know.
I see. So this is a phase that many solar systems might go through earlier on in its lifetime, but not necessarily recently formed. Is that correct?
Right. So you have your star collapsing from your cloud, and then you have a protoplanetary disk that's very gas rich. And over time, planets form and the gas dissipates, and you're left with a debris disk phase. And that will likely last through the end of the star's lifetime, though it might change a bit as the planetesimals collisionally grind into smaller and smaller pieces.
So the debris disk can linger after the main planets at least, have formed.
Right, exactly. Our own Kuiper belt and asteroid belts are sort of our debris disks.
Might be useful to put some time scales on this. It's true that planets form out of disks of gas and dust around young stars, but those disks dissipate in 5 or 10 million years. And so a star as old as Fomalhaut, which is about 500 million years old, you don't expect any of that to be left. So this is dust that has to form from a totally different process. And as Schuyler said, this is from collisions between small bodies in the system, and they pulverize each other as a result of the pulverization that are dust. The dust then drifts out into circumstellar space. The star warms it up, and then we see it in the infrared, and it can be very hard to detect in other ways.
Okay, and then after this inner disk, we have a gap, and then we have the intermediate belt. Now, do you think that this would be something akin to the asteroid belt?
Well, it's at a colder region, right? This is almost at 80 astronomical units for Fomalhaut. So it's not an analog per se to the asteroid belt. What's really neat about it is that we have this inner gap, which separates that inner disk and this intermediate belt, which is most likely formed due to a planet being in there and sculpting that gap. So we have an indirect evidence of possibly of a planetary object orbiting around Fomalhaut there.
When I first saw this image, it reminded me of those beautiful ring structures surrounding forming planetary systems that were taken by the ALMA, an array of radio telescopes in Chile. I realize ALMA is operating on a much longer wavelength, but any ideas to why it looks so narrow in ALMA?
Yes. So I guess there's two ways to answer that question. First, what is the difference between James Webb and ALMA? And the main difference is when you're looking at a dust disk like this, the wavelength you're using to investigate the disk coincides roughly with the size of the dust grains that you're looking at. So ALMA sees mostly millimeter size dust, which is less sensitive to things like radiation pressure that drives these smaller dust grains outward. Whereas James Webb, we're looking at things that are tens of microns in size, which are a little more sensitive to things like this. But we also know from dynamical modeling that this ring seen with ALMA is too narrow to be unperturbed by planets. So there's a planet likely that is causing this ring to be as narrow as it is.
Okay, so there's at least one planet there and it's sculpting the ring a little bit. And speaking of planets, I know that there was some talk many years ago about, hey, we found a planet around Fomalhaut, Fomalhaut B. And now I see, reading in the paper, it's referred to as the Great Cloud of Fomalhaut. So what happened to Fomalhaut's planet?
So just seeing the Fomalhaut B object with HST in 2008, that was a spectacular observation if you think about it. We saw something moving in scatter light observations with HST. So that was a spectacular observation. Unfortunately, follow-up observations with HST seem to show that object both fading, slightly getting extended, and on an orbit that seemed to show it leaving the system. So not really on an elliptical orbit. All of these observations hinted at Fomalhaut B possibly being a result of a massive collision producing a lot of small dust, which is why it was even visible in scattered light. Planets don't tend to be really visible in scattered light. This great dust cloud that you mentioned is seemingly a big clump of dust that's located within this outer Kuiper Belt analog ring. We don't know specifically what its nature is at this point. It could well be a background object, but it coinciding exactly with the ring is lower probability. So it's very likely a big cloud of dust also possibly produced by a large scale collision in that belt.
That rolls right into my next question. Where are the planets? How come we aren't seeing planets in MIRI? And is that a surprise?
So planets are really faint. In fact, planets that are less massive than, say, Saturn are below the detection limits, even for JWST. So you can move the dust around with planets like Neptune and Uranus, and they're the most common form of large planet around other systems. So there could be lots of planets in there whose presence is only made apparent by the rings and patterns like we see with Fomalhaut, and that we can't detect in any other way yet until we develop something even more powerful than JWST.
In your paper, you had deprojected Fomalhaut. So obviously, it's not truly an elliptical ring as we see it. This is a function of projection on the sky. How did you manage to create these deprojected images to make them look more face on?
Well, first of all, let's just say that this figure shows that we took images not only at 25 microns, but also at 15.5 and 23 microns as well. The 15.5 micron image and the 23 micron were taken through chronographs. And the 15.5 one is taken through what we call the 4-quadrant phase mask chronograph, which allows us to go to much smaller inner working angles. So we see the much hotter and closer in dust at 15.5 microns. And you can still see that there's contribution from the inner disk at that wavelength. The 23 micron chronograph has a very large blocking area. So that's not saturation. That is a chronograph literally blocking out the internal parts of the disk. To answer your question, I fitted the disk contours with orbital paths around Fomalhaut and just used those values to deproject the images. There's nothing particularly difficult about that part, but it does give you an idea of how the system would look like if you'd view it from above. And since George commissioned this one, maybe he should talk about it.
Well, all I did was insist it be done. Adam Block, who is a very skilled person with manipulating astronomical data to make spectacular but scientifically correct images. And so Adam did the heavy lifting on this. but it shows how the whole system is assembled. So you can see why the JWST image is so unique. If you go to what I call the assembly diagram, that kind of makes it clear which telescope did what.
That is spectacular. Wow. Might Fomalhaut eventually come to the point where it does start to settle down, have its planetary system, raise a family of planets, and get all that dust out of there? Do you think that's a likely outcome?
Well, Fomalhaut is an early type star, right? So it doesn't have too long of a lifetime. It's about halfway through or even further of its life. It's around 400 or 500 million years old. These stars live up to what, 800 million years. So it doesn't have that much more to go.
Thank you all so much. This is just exciting results and congratulations. And can't wait to see what you find out with Epsilon, Eridani, and Vega.
Thank
you very
We'll
much for
let you
having us.
know.
All right. Okay. I don't know what's going on here. I can't seem to find the pause on my recording, but I'm assuming it is recording. Good grief. My
It
pause
says you're,
control.
it,
It says we're
This is the
recording.
bla-
Wow.
this is the
it
blackmail
says
tape,
recording.
right?
Yeah, it's supposed to be. Yeah, except it's kind of hard to have a blackmail tape when you can't seem to learn how to run it.